Okay. Good evening. Welcome to the Vienna Gödel lecture 2025. I'm Stefan Szeider. I'm professor at the Faculty of Informatics, and I will guide you through this program. And yeah, today we have a great speaker, Hartmut Neven, and you already see the title here. But before I will have the honor to properly introduce the speaker, we will have two welcome addresses, one from our Rector, Schneider, and then the Dean of the Faculty of Informatics, Gerti Kappel. Yeah, the Vienna Gödel lectures we have now since 2013. It's easier to say the starting dates, so I don't have to do the math, how many we had. Started with Donald Knuth and very distinguished people, and I'm very happy that we can continue and have such distinguished speakers. And now, as we have the quantum year, the UNESCO quantum year is coming to its end, it's great that we can complete the celebration of the quantum year with this talk today. But without further ado, maybe I can ask now our rector to come to the stage.
Thank you. Thank you very much for the introduction, and welcome our distinguished speaker this evening who understands German, but I will still talk in English for all our guests. So welcome to TU Wien. We are really honored to have such a distinguished speaker here on board this evening, and I think Gerti will introduce more about your CV and your background. For me, I'm just arriving from a university strategy meeting with the ministry, where the whole of the Austrian community on the future of universities were discussing, and interesting enough, AI was one of the big issues, yeah, and one of the big topics. And what is for me very important in this context is, of course, that there's too little knowledge about it. So I'm really grateful that you all come this evening to this room. I was in the wrong room in the Kuppelsaal, and I was surprised that there was nobody there. And so I thought, yeah, maybe it's not that it could be the right room. It was just an error in my agenda. But there's really not enough knowledge about it and what it can do and what it cannot do. And I believe this now combined even with the quantum and the quantum era, I think this quantum year is just the beginning of things that will happen in the future. But things get more complex. And if I see our quantum researchers from the physics also being present here tonight, it's even more difficult to understand it even combined. So I'm really curious myself about your talk, because there's this saying that I'm, as a civil engineer, always listen to the physics professors, that they say they cannot explain it, but it is like it is. And I'm really curious about your explanation. One of the big things that is discussed on the society level, of course, in this context is, can AI take responsibility, and can AI serve as a role model, for example, in the teaching? And I really doubt this, a role model and the personality. And this is why your example as a human also shows this difference. I believe what is transported in knowledge and in the background beyond the pure knowledge and expressed beyond something we look on YouTube shows that we still, and hopefully, and I'm convinced of this, although in the future, need this human interaction to understand the things properly. And it is not enough just to listen to it on YouTube or on the videos. But of course, this discussion has been there when the radio came, it was there when the TV came, it was there when the computer came, it was there when the cell phone came. All the time we had disruptive technologies that come up. People were fearing, of course, that they become obsolete and other things will take their place. To a certain extent, this is true. To other extent, not. And this is why I'm curious. Finally, I just want to make the link to our TU Wien Future Fit strategy we just finished this year. And I also brought one copy for you to have a look, because there's one line, I like all the lines, but one line I really like. It's the first line. The vision of TU Wien for the future is TU Wien where we dare to reason. And this is exactly what it's about tonight also, I believe, to dare to reason. And this combined with our mission that we do technology for people and not technology for technology is something I believe that we are all very much dedicated here at TU Wien to bring this knowledge into a good context for humankind to evolve. And we need you, we need the teachers, we need the people that know into the detail how we can really bring it to the best of our developments. And this is why I'm really grateful that we have such high-name speakers like Hartmut Neven tonight here at the Gödel lecture, which is a very distinguished place to do it. So thank you very much. Thank you for all your attention tonight. And now I will hand over to Gerti. Thank you.
Thank you. Ladies and gentlemen, our rector already mentioned this. You know, we are celebrating the United Nations Year of Quantum Science and Technology. Why are we celebrating it? 100 years of quantum physics. So what happened in 1925? You all learned it in primary school or secondary school. Schrödinger did his Schrödinger equations, for which he got the Nobel Prize in 1933. And the rest is history. And I guess the kind of the end point of the history, which is the present today, we will hear today in the evening. We have celebrated the last 3 days the AI Festival at TU Wien, and showcasing our research, our industrial innovation, and also what we do in terms of science communication and outreach. Of course, we can't look back for 100 years because, you know, artificial intelligence was in 56 and it was not in Austria and not in Zurich. It was in Dartmouth where the first time the term was coined. But at least it's almost 40 years that we had the first professor on artificial intelligence at TU Wien. Notably, today we would say symbolic artificial intelligence. But nevertheless, since 40 years, TU Wien and the Faculty of Informatics is doing research in the broader area of artificial intelligence. And also, as our rector said, we have to be very careful when we do our research and when we talk about our research. Because on the one hand, especially the symbolic AI, the logic-based AI, where we not only dare to reason, where we do reasoning, a lot of reasoning, this can be certified. There we have our rule system. But we know when we today read AI in the newspaper, it's either an algorithm, okay, checked, deterministic, we can do it, or it's really machine learning. And then it becomes a bit spooky because almost everybody says, at the very end, we don't know how it works. And I think here is where especially the cluster of excellence, bilateral AI, which has been established in Austria and where TU Wien is working together with other 5 institutions in Austria, where they really have the responsibility to not kind of hide away and do their research in somewhere in the cellar, where they really have to kind of take the responsibility and find answers how to explain the unexplainable. And I think this is something where it's very important that we do our basic research, but that we also go out and do the demystification as we have done over the last 3 days. Now, what would be the best end of a quantum year in Austria, where, you know, quantum physics, it is not 100 years ago, or as a bit less, that there was the Nobel Prize in quantum physics. It was just a couple of years ago when Zeilinger got the kind of, you can say, the next one in this area. What would be the best of ending a quantum year and a 3-day of AI festival? Of course, we combine the two. And I also have to kind of second our rector. We are very happy that we have Hartmut Neven here talking about quantum AI. He will be introduced by Stefan Szeider. But what I want also to mention is it's not by chance that we took this topic as the end of the AI festival and of the quantum year, because especially the TU Wien, the Faculty of Physics, Faculty of Electrical Engineering, Faculty of Computer Science, as a Faculty of Informatics, we have joined our forces over the last years and have established an interfaculty, interdisciplinary master in quantum information science and technology. And when our rector always says computer science are kind of the black sheep of the maths area of mathematics, I can tell you it's even worse. We are the underdogs of the physics. Yeah? Because of course, the physics, they know everything. And I remember in September 2020, when at that time the dean of the Faculty of Physics came to me and said, Gerti, we want to do a master in the area of quantum information science and technology. And of course, we don't need computer science. We know everything by ourselves. But we went to IBM and Google, and they said, where do you have the programmers? Where do you have the software developers? You need people. The future has to understand algorithm. So therefore, I'm here and, okay, let's do together. So we have this master, we are working together, and I'm very happy that we have Hartmut Neven and that we have all you here as participants, enjoy the evening and ask all questions. I can promise you, you will get answers. Thank you.
All right. So we all are now, of course, very eager to hear the talk. So I need to torture you for a few more minutes to introduce the speaker. Hartmut Neven is the founder and lead of Google Quantum AI, and also the vice president of engineering at Google. So I think they're quite important positions. And I think Hartmut is a real pioneer. So he coined the terms quantum machine learning and quantum AI. And there is even a scaling law that bears his name. Similar to Moore's law, there exists a Neven's law. So I think in 2006, he joined Google by acquisition of his own company. And already in 2007, he and his team implemented the first machine learning algorithm on a quantum computer. Then in 2019, there was a breakthrough result because they showed that they could solve problems on quantum computers that are not within reach for practical computation on classical machines. Now, more recently, in 2023, another breakthrough was to show that quantum error correction works in practice. And seeing the title, I assume this will be covered in the talk. So, in other words, his lab has repeatedly shown that and demonstrated things work on hardware that theories only imagined on paper. So Hartmut's intellectual journey spans physics, economics, and computer science. And he studied on several continents. And he also was a recipient of Germany's most prestigious academic scholarship. And he completed his doctorate in physics in 1996. now you think, okay, now hope he's done. I also need to mention these other things beyond quantum he did. So he co-founded and founded companies who were leading and pioneering in facial recognition login and in visual search from mobile devices. And at Google, he co-founded Google Glass. Okay, so throughout his career, Hartmut has consistently pursued questions at the edge of what is known, often years before it entered the mainstream science. And so I assume, I hope that today we will get not only an overview of the current state of quantum computation, but maybe also a peek into the future, what we can expect in the next couple of years. So I'm delighted to welcome, and please join me welcoming Hartmut Neven.
Ja, schönen guten Abend und vielen Dank für die Einladung. I realize we speak English here, so I will switch. So yeah, nice, good evening, and I'm very flattered to have received this invitation to give the Gödel lecture. And this is not just for me. I feel I'm representing my team here because the results you're going to hear about tonight are from the Google Quantum AI team as a whole. And after these nice introductions, of course, I'm the gun to explain you why quantum AI, that is AI aided by quantum computing, is maybe even more interesting than AI already is. And in particular, I want to also tell you a little bit about the current era. There was a little bit of a sea change in quantum computing. We are now entering the era of error-corrected quantum computing, and I want to explain to you a little bit what this is about. So the mission of Google Quantum AI is easily stated. So our mission is to build quantum computing for otherwise unsolvable problems. So how do we do this? A number of years ago, after this important 2019 results that Stefan just mentioned, we put out a roadmap. And this roadmap has been tweaked a little bit over the years. In particular, initially it only started with a hardware track, but now we also have a software track, and there's an access track. So how can you access Google's quantum computers? And let me tell you a little bit about the first track, the hardware track. So we broke down the challenge of making a useful quantum computer into 6 big milestones. And the end of the journey is, we call milestone 6, is a machine with about 1 million physical qubits, which we can orchestrate to become several thousand very well-protected logical qubits that can execute rather complex quantum algorithms. So this is still a bit out, but we already, out of these 6 milestones, we achieved already 2. The first was in 2019, where we showed for the first time that there is a benchmark computation that at that time a quantum computer could do in minutes, but the then best supercomputer running the then best software would have taken 10,000 years to do. Yeah. So making essentially good to show for the first time, hey, there's some stuff that quantum computers can do that classical machines cannot do. And then we proceeded to our next milestone, which is to show that quantum error correction works in practice. I know quantum error correction sounds a little bit boring. It's almost like trash disposal. Who wants to deal with errors? But unfortunately, it's a key technology to make quantum computers scale. And I will talk a little bit more about it. We are now at a stage roughly the halfway point of our roadmap. Our next goal that you will hopefully hear about, or next milestone you will hopefully hear about not too long from now, is milestone 3, which is one really good logical qubit that has an error rate of 1 less, or 1 in a million or less. So how would we get there? So here is a typical data from a typical experiment that shows this technology, quantum error correction. So why is this relevant and how do we do this? So quantum information has a tendency that it easily leaks out. It involves systems in the environment. So the information essentially leaves your processor, leaves your quantum computer, goes into the environment, and by definition, the environment you can't control. So now there is a loss of control over your computation. You lose information. So in order to prevent this, we need to make our qubits more robust. And in engineering, it's always the same story. How do you make things more robust? You make them more robust by introducing redundancy. Yeah? You want to fly, let's say, to the US. Yes, you can do this in a one-engine airplane, but it's definitely safer if your airplane had 2 engines, or if it's 4 engines, even better. Same story with qubits. If you want to make one good logical qubit, you distribute that information over an array of physical qubits. And then the bigger your array becomes, the more robust, the more stable the quantum information of your logical qubit should be. Yeah? And so what you here in this inset, or what is shown here, are these arrays. So we use a technique, it's called the surface code, and there you distribute your logical qubit information over arrays of 3 by 3, or 5 by 5, or 7 by 7 patches of physical qubits. So those numbers we call the code distance, 3, 5, 7 in this case. And then what you want to see is something like in this, shown in this inset here, that as you make the code distance larger, the logical error rate shown here on the y-axis should get smaller. Should be suppressed each time you get bigger. And when we did this for the very first time, that was 23, we achieved it, but we achieved it just by a hair, that as we went from 3 by 3 to 5 by 5, the error came down, but just a little bit, a few percent. So the community wasn't too impressed when we showed it, but we were very proud and we worked really hard on it, because the theory for quantum error correction was already known for 30 years, but it had never worked in practice. Because, see, it's a scary proposition. As you make your arrays larger, you have more qubits, you have more gates, you have more measurements. There are way more error processes that can happen, and it's by no means guaranteed, or what happened before, that actually the error didn't come down, the error went up. So we were very happy to see that at least the error didn't come down and it went slightly down. And then this is data from a repeat experiment from 2024, where we did it again, but this time was already a bit more impressive. Every time we increased the code distance, the logical error rate came down by a factor of 2. So you can see here, for example, that we run, essentially, it's a memory qubit. It's just sitting there. It's all it's supposed to do. Don't lose your information, please. Just sit there. And then you see that as we go, and here you see again logical error rate. Of course, it grows over time the longer you run it. It's not perfectly protected, but you see that as the code distance increases, so here the red is 3, and you come down to this line, and then here to the blue, the error rate come down. And also importantly, a physical qubit alone would be here. So we went past the break-even point. So the logical qubits are now really better than the physical qubits themselves. So we achieved what we wanted to do, preserving the quantum information by introducing redundancy more robustly than you would have done otherwise. And that essentially addresses sort of this 30-year-old challenge. So Alexei Kitaev, who came up with this scheme for the first time about 30 years ago, is now part-time on our team, and he said, oh, great, you did it. I set this out 30 years ago, but now you reduced it to practice. We did another experiment that has gotten less attention, but I think is equally interesting and important. You know, a qubit, hopefully most of you know what a qubit is essentially a two-dimensional object. Yeah, you can, how we typically visualize it, by a vector and a sphere, the so-called Bloch sphere. And so you have two angles that determine where this vector is showing. So you have essentially two channels against which you need to protect. So we call those bit flip errors and phase flip errors, and you need to protect against both. And the surface code conveniently, it's a two-dimensional code, can conveniently do this. But because our chips are not so large, we couldn't go much larger than 7 by 7. So 9 by 9 wouldn't already not fit. But of course, what we could do instead, we just say, oh, we protect just against one of those 2 degrees of freedom we protect. And then we can make a one-dimensional code, and we can go to a much longer code distance. We could go all the way here to code distance 25 in a code format that's called the repetition code. And then what you saw there is something, or what is shown here in this inset. And again, same game, you make the code distance bigger and bigger, and then you look how your logical error rate is coming down. And you see here that it's coming down quite a bit. It comes down to 10 to the minus 10, so 1 in 10 billion. So that's kind of good news, because that means if you had this in 2 dimensions and you had an error rate as low as 1 in 10 billion, that really means that you can run algorithms with 10 billion steps. So that's a pretty healthy, robust algorithm. And so in some ways, all we need to do is to repeat what we see here in 1D, in 2D, and then we are kind of done. I mean, I'm glossing over a few other elements, but it's very encouraging that we can get with the error rate down that low. And you see it stops there. However, there is a noise floor. Actually, the earlier 223 experiment stopped here. So that earlier we understood this is actually coming from cosmic rays. So when there are muons coming through our quantum processor and they shake the silicon, so there are phonons in the system, that messed up our qubits. So we are literally, the computer is that sensitive that it is feeling space weather. If there would be a muon shower coming by from some supernova outside in space, the computer would feel that. And then, of course, you might think, oh my God, how can you ever build a robust machine? But it turned out we were able to build traps for these phonons and essentially capture the deposited energy. And as you can see here, it's less of an issue now, so we come deeper much lower. But here's, again, a new noise floor. And we don't know what it is yet. There may perfectly be some new physics. I mean, fortunately, it's that low that it won't bother us for a while, but something is still going wrong, and we are not exactly sure what it is. So here you see a little bit the key specs. This is more for the experts in the audience. So if you look in the middle column, it gives you sort of the typical sort of spec sheet, you know, look what my quantum computer can do. So the coherence times are, we typically give mean or median times. So it was close to 70 microsecond T1 times. The 2-qubit gate error rate, an important number when judging how good quantum computers are. So this was approaching not quite 3.9 fidelity. And another important feature of superconducting quantum computers is that they're very fast. You can do high repetition rates. So we could do almost 1 million measurement cycles per second. And of course, you need such high repetition rates if you want to measure. How would you measure an error rate like 10 to the minus 10 before you see this, you need to do a lot of repetition to have the statistics to even see that. So some other quantum computation modalities would have a hard time measuring this even. And then, our pride was that lambda, this is called the error suppression factor, essentially. As you go to a higher code distance, by what factor does your logical error rate come down? And this was there a factor of 2. So that was about a year ago. The chip was called Willow. Oops. And it had 105 qubits. And our chips are organized like a checkerboard in a 2D array. But since then, we have seen further progress. So we built larger processors. So we went from 105 to 500 qubits. We made the T1 time, or I should have maybe said this is the is one of the coherence times that essentially tells you how long does a quantum mechanical superposition state stay in place. And of course, quantum mechanical superposition is sort of the magic ingredient that makes quantum computers more powerful. And then if you look here, you see in 22, the median here, these are cumulative curves. So you see the T1 times as a CDF curve. And then if you look at the median point, you see it was about 20 microseconds. So it wasn't so great. Actually, other groups in the field had much better coherence times than we had at Google. However, we pride ourselves, or not pride ourselves, quantum computing is really a system engineering game, and all your components have to be good. So there are groups that have more qubits. There are groups that have, if you go to their best qubit, have much longer coherence times, and. But what we always emphasize is, and this was sort of instilled into the team by one of the founders of the hardware group, John Martinez, who actually is going to get the Nobel Prize next week. The 10th, I think, is the ceremony in Stockholm. So he always taught his students, you have to be good in system engineering. So to do these, like the 2019 experiment or the 2023 experiment, these are really exercises that only work if all the components of your system work well together. And there you have to do engineering trade-offs. Sometimes you have to forgo some coherence time in exchange of, let's say, a faster readout or a faster reset. But we have improved since then. So you see median time 22, 24, 25, and now we are here. So we are, it's almost a factor of 20 better coherence time. So that bodes pretty well for the development of our processors. To make this a little spicy, also put a competitor curve in there. You can, I won't say who that is. So we are now reaching a logical error rate. It's now approaching 10 to the minus 4. And just to remind you, our milestone 6 is to reach 10 to the minus 6. So still 2 orders of magnitude to go, but yeah, getting there. And this is unpublished internal information, so far not shown in a paper. I told you how we went from a lambda of about 1 or a little bit better than 1 to 2 over a year, but now another year is over, and we are now approaching 4, which is really showing there is very rapid progress in the quality of the qubits and the processors. And then other improvements, again, it's system engineering. We have now nicer cryostats. So unfortunately, I can't show them anymore. So this is an older one, but the new cryostats can hold way more qubits. So with current technology, they can hold 10,000 qubits. And moreover, they're modular. So you can stick them together to make sort of bigger and bigger machines. And another area, actually one that gives us the biggest headache, you can actually see this here still in the previous picture. And you don't have to be an ingenious engineer to realize, oh, wait a minute, is there not a problem? Currently, every qubit and every coupler of the qubits needs its own control line. So that's a lot of wires. So this was for a 105 qubit chip, and the dilution refrigerator or cryostat is almost full. So obviously that can continue. So what you need to do is you need to come up with better wiring strategies. And actually the thing that holds us back from reaching milestone 3 is not so much the quality of the qubits or their coherence. It is very mundane issues such as how do I get enough wires down to our chips. And one technology you develop there, you make much skinnier wires. You go away from these big fat wires you saw in the previous pictures to what is called flex wires. These are very skinny sheets that have many wires in each sheet, and then you can stack these sheets together. So actually in a sort of diameter about my pinky, or that cross-section, I should say, I can now send with these new flex wires down as many signal lines as all the signal lines you saw in the previous fridge. But there are other strategies. You can do multiplexing. Do you really have to send a different signal to each coupler? In particular, in quantum error correction, you often do sort of these orchestrated operations. You can just reuse certain signals. It's called multiplexing, so that might buy you another factor of 10 in wires. And then there is sort of the most luxurious royal solution that is currently our control electronics sits next to the cryostat. So it's big racks of DACs, digital to analog converters that make sort of the waveform signals, the microwave pulses that we send down to our qubits to control them. But it would, of course, be way more elegant if we could make those control signals at the cold stage. So then we just send down a digital line with instructions for a processor that lives right next to the qubit chip. You make this sandwich chip, and the second part of the sandwich has superconducting control electronics that then can make the control signals on demand. And if that were to work, it's risky. Old timers on my team, they tell me like, this has been promised to us since the 70s. This has never worked. So don't hold your breath for it. Well, we just acquired a company called Atlantic Quantum. It's a spin out of MIT and Harvard, and they specialize in this technology. And hopefully they come through, because if they do, then one of our fridges could already hold 500,000 qubits. So to get milestone 6, we would just have to stick 2 fridges together and we would be done. Okay, so already explained this to a good degree, but maybe very quickly. Again, this is the same picture, code distance versus logical error rate. Here you see the 23 experiment. So it came as we went from 3 to 5, it came barely down. This is the experiment of last year, where we went from 3 to 5 to 7, and it came down steeper. So you have your quantity and quality. And quantity means more qubits, larger code distance, and quality is how steep do you come down. And now we are approaching 4, but because of the issues with the wiring that are not fully solved yet, we made great progress, but it's not properly working yet. But the processor, to our surprise, so what originally I had predicted was in this chart. I actually like to show to our CFO when we go and ask for a budget and say, here, you can track us. We just watch how our processors go here from endpoint to endpoint to endpoint. But what we, somewhat to our surprise, noticed that what we thought is the hardest thing, this is improving the coherence of our chips, was easier than just making bigger systems. So now we are thinking, rather than going to, let's say, a code distance of 17 or so to reach our milestone 3, if we can make lambda yet bigger by a factor of 2, then we can already achieve it with just an array of 9 by 9 or 11 by 11 more compact arrays of physical qubits. And that is at least how it looks like right now. Then on the hardware side, some rapid fire updates. Again, it's more for the experts. When you make a quantum chip, you can never assume that you have 100% yield. There will always be some qubits that are broken, and you have to now develop error-correcting codes that take this into account. So we have a strategy called Lucy that is designed to deal with such dropouts. And another development that is happening is this, actually you earlier asked, oh, the physicists can do this all. It's actually not true. I'm a physicist myself, but you need computer scientists and people who understand good old computer architecture, because what we see if our algorithm team together with our quantum error correction team thinks really end to end, how would we implement an important algorithm, let's say some quantum simulation of some chemical reaction, then you notice things that in hindsight, of course, are not surprising. Some qubits you hardly touch, they're just sitting there, they're rarely used in your algorithm, so they look more like memory qubits. There are other qubits that you touch very often. So you may not want to use the same encoding structure or strategy, I should say, across your whole set of qubits. So what's happening is there's genuine computer architecture emerging, and it starts to look different than just a large ocean, initially we literally envisioned we would make just one huge sheet of silicon. We have our aluminum qubits on top of it, and that's our machine, but it's unlikely to look like that at the end. So, of course, how to best organize your processors and how to couple them, and whether you need long-range connection or just nearest neighbor connections between your qubits, this is really largely determined by insights from computer science. Okay, so this was the update on the hardware side. So now let's switch to the second track, software. And here the story developed as follows. So after this 2019 experiment, where we showed for the first time again that a quantum computer could do a benchmark much quicker, we got a lot of criticism. People said, oh, you haven't tried the very best techniques to run this on classical computers. If you would have done this better, it wouldn't have been 10,000 years, it would have been much shorter. Now, it turned out that it took many years, and it's actually an interesting story. It was a worldwide effort, people trying to improve software. This goes by the name of tensor network methods. These are the go-to best methods for simulating quantum circuits. And then, for example, Alibaba found a new memory technique to store the large tensors more efficiently. A researcher at Caltech found a way to break up the large tensors with methods that come from social network analysis. It was beautiful science, and it took many years. And indeed, the times came down. Actually, our paper predicted this already. Actually, if today you would run the same benchmark again, let you guess, maybe you know it, it would just take 6 seconds on a supercomputer to do the 2019 benchmark. But what has also happened, first, the improvement of algorithms stalled. So tensor network methods have reached looks like an asymptotic state. They're not getting better every year anymore. And in the meantime, our processors got bigger, and even more importantly, they got better. We could run gate operations, algorithmic operations with lower error rates. And this benchmark that we use, by the way, it comes with a name. It's called random circuit sampling. So this is our go-to benchmark, and it's a nice tool to compare quantum processors against each other or quantum processors against classical processors. And now what we found is that last time we did it, it was literally off the charts. So this is a year ago. So doing this computational benchmark, then on the best classical supercomputer, using the very best tensor network methods, would have taken 10 to the 25 years. So this is 10 septillion years. So yeah, a 1 with 25 zeros. So a completely impossible amount of time to do this task on a classical computer. And now nobody said anymore, oh, you could have done this better. I mean, probably you can still do it better. You shave off a few zeros, but it's still impossibly long. So this is a task that classical computers will never be able to do. And actually this curve here, as you mentioned, Neven's law, so to say, this is a double exponential over time. Essentially the amount of effort it takes to simulate a quantum processor for over time grows at a double exponential rate. So this is really insanely fast, and you can see it from 10,000 years a few years ago to 10 to the 25 last year. And for the latest processes, this keeps going up. So, but then the criticism became, oh, yeah, it's a little circus trick. You showed on a benchmark that your quantum processor could do something that classical machines cannot do, but who cares? This is not really important or relevant. It's not a problem that people on Main Street have. And very true, we have never said this. There's no known use for random circuit sampling other than for benchmarking. But we had other efforts in parallel where we essentially made good on what we call Richard Feynman's dream or Feynman's killer application. Because Richard Feynman, actually, he was responsible for what today we would call a data center. We had some computers, which were literally humans, armed with some computers, and he realized that certain rather basic computations, like computing the ground state configuration of a molecule, would take time that he would never have with any computer that you could ever think of, unless you make this computer also quantum. So there's this famous quote, I'm sure you have all heard it, nature is not classical, damn it, and if you want to simulate nature, you better make it quantum mechanical. Yeah, and we made essentially good on Feynman's dream. So here you see a bunch of papers, actually all of them high impact, nature or science, and the style of this work is always the same. You make an interesting quantum state, and then you study its properties. Yeah? And then we have already made proper scientific discoveries. Actually, we nickname them discoverinos, because these are sort of small discoveries that wouldn't get you a Nobel Prize just yet. But still, we have done things like studying time crystals or non-abelian anyons, or the properties of a holographic traversable wormhole. So interesting physics could be studied and was studied. Interesting enough that the Nature editors say, sure, you can publish this. But all of this work so far was of the nature that you could still, the number of qubits used and the number of gates used was still too small in the sense that you could have still run this on a classical machine. So the outstanding challenge now was to combine it, make something, show us an algorithm that is A, only doable on a classical computer, so it's beyond classical or classically intractable, and show us that it's useful. And we made a good step towards this 2 months ago. Some of you may have seen it. It graced the cover of Nature. We published an algorithm we nicknamed Quantum Echoes. And it's sort of, can think of it as the first useful beyond classical algorithm. And let me explain a little bit to you how this works. So first, let me explain you the challenge. What do you need to do if you want to run a quantum algorithm that is hard for classical machines? It needs to be complex enough. You need enough qubits and enough gate operations so that this is, let's say you use this in a quantum simulation. You simulate some molecule or you model fusion plasma or some Feynman type quantum simulation. So you want a big enough quantum circuit. But now there's a challenge. If you take a typical quantum mechanical observable, let's say the magnetization of one spin, or it can be a multi-qubit, or sorry, when I say spin, qubits and spin often use exchangeably. These are both two-level systems. So you can have an observable that involves several qubits. And if you look at such observables, you will find that for a typical circuit, the signal you measure is coming down. Yes, there's a complexity as you make your circuit bigger. The complexity for classical machines grows. But a typical observable becomes smaller and smaller. Why? Because now you build more and more entangled states. An entangled state is this big sum over classical configurations. And now things average out. Let's say you want to look at the orientation or magnetization of your first qubit. Let's say the first term in your superposition is 1, 0, 0 something, but the next term might be 0, da, 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 something. So it starts to average out. So what happens if you are not careful is that your observable or your signal also gets down exponentially. And now you have a problem because you have to draw to get enough statistics. You have to draw many samples. So, and this is fundamental. You can't take this away. On top of it, there's of course experimental noise that makes it even worse and has your observable signal wash out even quicker. So that's why so far nobody has been able to show a computation on existing machines that fits this bill, that it's useful and beyond classical. And by useful, we just mean if you can't measure any local observable with good signal, yeah, then forget it. What do you see? You will just measure all zeros. But there's a solution. And the solution is to refocus your signal. And if for a moment you just look here at this U, so this U is a unitary that is realized by a quantum circuit. So underneath this box here, so here you have your qubits, underneath this box you have a bunch of, let's say, 1 or 2 gate operations. And by refocusing, we mean you just, at some point, you stop and you run, instead of measuring anything right now, because then you have this problem of very low signal, because now you are deep in Hilbert space. You have this huge superposition, observables averaging out, but you don't measure there just yet. You just turn your circuit around. You invert all the operations you did so far, you do in reverse. So basically you come back now to where you started. You refocus your signal. So in quantum mechanical calculus, you do U dagger. So that's basically you implement the identity, and you now should see strong signal again. Actually, what we typically look at these experiments, we look at the correlation of the qubit in the beginning. If we pick out one qubit, we call this our probe qubit or measure qubit, and we measure its state at the end and at the beginning, and we look how it's correlated. And this is called an out-of-time order correlator, or TOC. So this is really the technical term for quantum echoes. So, but you may wonder, why do you do this? There's no point. You do U dagger, that equals to the identity. So you just implemented an identity on your circuit. That's not interesting. Indeed, that is not interesting, but now you're set up to do something interesting. And the interesting thing is to do in the middle, when you're deep in Hilbert space, now you tickle or put a gate operation on one of your qubits. And then far away, you have this probe qubit, and it is now there to sense how the effect of this disturbance, we call it the butterfly operator, and no essentially relation to butterfly effect in chaos is intended. This is actually closely related to physics here to the physics of chaos. So you look how the signal from the butterfly operator propagates to the probe qubit. And for people who are not familiar at all with quantum computing, or if I explain this to my kid, hey, Dad, what are you working on? The perfect way to explain this is sometimes at night we sit in a whirlpool in California, and then I save the money to heat up the big pool. It's sitting there cold and just at night, and then the surface of the pool very quiet. So perfect place to explain quantum mechanics and interference. You tap on the water, it makes nice waves. You tap a second, and now you have two circular waves, beautiful interference pattern. And now you can understand what this algorithm would do. See, if I tap on the water and the wave, so this disturbance goes through my pool, and I have, let's say, a probe at the very corner of the pool. See, the way this wave arrives there would be different if the pool would be filled with water or oil or honey. The wave propagation would be different. So the probe can pick up information about the material. And this is sort of the same here. You just do it in Hilbert space. This setup where, again, the recipe, how this algorithm run is you start at an easy-to-prepare state, then you apply a unitary, you go deep into Hilbert space, then you tickle a qubit, you refocus, and far away you try to listen, how is the effect of this butterfly operation reaching me? And that teaches you something about you. You can learn properties of you this way. And here I wonder whether this is a notch too difficult for this audience, but I want to explain the following. You see, from the butterfly operator, there's sort of this wave that goes through Hilbert space, and you try to catch it. So our chips are not that large. If you have 105 qubits, this wavefront cannot travel too far. You can make it in the furthest corner. So your circuit doesn't have to be that large before you reach it. And maybe it's not large enough yet to be classically hard. So we were stuck there, and damn it, we need bigger chips. That's, of course, not so easy to come by. So we thought, why don't we do the following? Instead of catching it right the first time, we just wait. We go, a picture of this, yeah, here. You go forward, you go backward, you go forward, and you go backward. So you repeat this. And this is known as an out-of-time correlator square, or Otok square. And now, because the wave travels through the medium longer, you pick up more information. And moreover, what also happens is that the interference that happens, because now you can have longer paths, Feynman paths, that need to interfere. So in Otok square, you have much more long-range interference than just the original Otok, where you go back and forth. And there's some math where you can actually see this. If you write down the formulas for this is the Otok, and this is the Otok square. And these are these huge sums, so these coefficients C here, these are real valued numbers, and these are the traces over two Pauli matrices or a product of four Pauli matrices. And you need to ask the question, which terms contribute to these sums? And then you see, for this term here to be non-zero, the two Pauli matrices have to be the same. This is a rather strict condition. While here for Otok square, this here needs to be the identity. And this you can reach either, again, similar, that the first and the second Pauli operator is the same, or the third and the fourth is the same, or there's another possibility. You just pick alpha, beta, gamma, and then you just choose delta such that you make a loop. You need to make these loops out of those Pauli operators to have a non-zero term here. And this condition here is much weaker. So you have much more opportunity for interference. So Otok square is much more sensitive, or is a much more quantum signal, because you have way more interference interfering paths that create your signal. And initially, when we submitted this paper to Nature, the Nature editors were not very happy. They said, "Oh, what the heck is this? You know, like you had to do this just because your chips are not big enough," and they were not very pleased. But then Michel Devoret on our team, who also will get a Nobel Prize next week, he said, "No, you don't understand. This is not a bug. This is a feature. This is like in physics, where you go from a single pass interferometry to multipass interferometry, and it becomes much more sensitive. You do interferometry, multipass interferometry in high-dimensional Hilbert space, and this is a very sensitive tool. You cannot, in a way, think about typically this metaphor completely falls flat, but in this audience, you know, it's like LIGO for molecules. It's a very, very sensitive probe where you can learn about molecules. And this brings me to the last piece. Hopefully, I convinced you that the OTOC signals are classically hard to do. By the way, of course, the simplest way to check this is you do red teaming. So we had a group of 10 computer scientists that worked. We put 10 person years into this to run the best possible classical algorithms to check how long would they take on a classical supercomputer, and they couldn't do it. And then also, I should mention this last thing, when you run those circuits, there's actually an interesting experimental test you can do that you really have a signal that's constructed by quantum interference. And how do you do this? You put in, we call it a cut. In the middle of the circuit, we put on each qubit a single gate operator that just dephases it a little bit. And if your signal comes about by quantum interference, then if you have this dephasing, now sort of your nice constructive interference doesn't work anymore, and your signal comes down. So this is an interesting experimental probe to check that quantum interference was really relevant to make your signal. And then we could see for OTOC, we had some sensitivity, but for OTOC square, we had more sensitivity. So in some ways, this is the first quantum algorithm that was discovered with the help of a quantum processor. Nobody thought about OTOC square when we started out. Yeah? So what came as and maybe interesting also to see overall, to develop the quantum echoes algorithm, we ran 1 trillion circuits. Just to give you a sense, this is probably about 10% of all quantum circuits that humankind ever ran to date. So it was a massive effort. And of course, this also shows one advantage that you have in using superconducting qubits. So they're very fast. You know, for many technologies, if you ask them, hey, do a trillion runs, there's just no chance. It would take them hundreds of years to do. So, and I think this will be typical. See, my colleagues in classical machine learning, they don't design neural networks from first principles and, oh, we know, you know, by piece of paper how this has to look. It's very empirical. You try this architecture, that data set. So you try a lot. And here, in some ways, we tried a lot too before this algorithm was ready. That's how computer engineering typically proceeds. But that shows this trial and error only works, of course, if your machine is fast enough that you can try many things. So therefore, what we call prefactors, like how quick is your clock cycle, is actually quite important characteristic for a quantum processor. Okay. I now hopefully really convinced you that quantum echoes is classically expensive, but why is it useful? Now it's useful, or you can make it useful by choosing this U, not just arbitrary or randomly. You can make this U such that it expresses the evolution of a quantum system. So you make it, the U is equal to e to the I ht, where h is a Hamiltonian describing your system. And then you can do the following. You can go to a real-world system, like an NMR machine. And in an NMR machine, you can actually also run these time reversal protocols. And let's say you put a molecule in there that you sort of know what atoms it's made of, but you don't know exactly. For example, we have a companion paper that shows a molecule that consists of 2 phenyl rings, and chemists didn't know how are they rotated relative to each other. And then we put this into an NMR machine, we ran OTOC and get a signal. And then we go to our quantum processor and we make an ansatz. We say, oh, we know it's a phenyl or a diphenyl, but we don't know this angle, theta, so we keep this as a free parameter. And then like in machine learning, you just do a gradient descent on theta such that the OTOC signal or OTOC square signal you get on your quantum processor equals the OTOC signal you get in NMR. And if you can make them to coincide, then you say, oh, must be that theta. So I learned something about this molecule. So this is proper quantum machine learning. So these time reversal signals, even though NMR people could have used them since decades of years, without a quantum computer as a tool, you couldn't have made sense out of these signals. So there is a new protocol now available for NMR. And that's, I'm not sure I should say this, somewhat a big deal. There have been 4 Nobel Prizes given to new methods in NMR. So it's, of course, a very important tool we use. And I don't know, we don't know yet whether in practice this really turns out to be super beneficial. But in principle, here's an algorithm and a new game you can play, essentially quantum computing aided NMR. Let's see where it takes us. Okay, so on the software side, 2 more quick updates. So this was our main achievement, the first useful beyond classical algorithm, but other things have happened as well. So for example, one of the more problematic applications of quantum computing is, of course, its potential for cryptanalysis. And we have always kept a close eye. What is the minimum resources required to do cryptanalysis, for example, for 2048 RSA codes? And we have this wunderkind on our team called Greg Gidney, who sort of excels in setting new world records. So he had the old world record where he showed, oh, you need 20 million physical qubits. But then earlier this year, he came up, oh, we only need 1 million physical qubits. And that's relevant because I showed you our roadmap in the very beginning. The endpoint of our roadmap is a 1 million physical qubit machine. So this machine therefore becomes cryptographically relevant. And of course, those in the know sitting here will think, oh, wait a minute, my Bitcoin, I don't know if Bitcoin is actually secured with just 256 elliptic curve cryptography. Seems like you should be using less qubits for that. Yeah, so which is a correct guess. And so the message here is people who care for keeping their data safe, they should not think, oh, this is decades out. It's probably much shorter than 10 years before today's cryptography schemes will not work anymore, and migration should happen yesterday. And because it takes time in practice to establish new cryptographical schemes. So similar improvements have also happened with Feynman's killer app in quantum simulation. So the times here in this graphic, you can see the year and then how many gate operations were needed to do. Let's say this is here another benchmark we like to use, a FIMOCO molecule. Analyzing this is relevant because it helps with nitrogen fixation, a very important task for humans when you make fertilizer. And you see, the original algorithms were not that good. You had to run it even on a quantum computer 100 years, but then came down more. And now we are sort of at reasonable times. So the story is the same. On the hardware side, we have more qubits and better qubits, so we can run more complex circuits, or we can provide more quantum computational volume, as we call it. And on the algorithm side, things become more and more efficient. They need less and less complexity, less and less gate operations, and these two times sort of cross. So the first useful algorithms, the time horizon is moving in on us. Okay, maybe, yeah, this is really also only for experts. One sentence: there used to be an operation, it's called T-gates in quantum computing, and making T-gates has been a pain. So this was really an engineering abomination. Here, you just see the complexity of this. This was the circuit needed to represent one T-gate. And oh my God, it's called a T-factory. And this is really super inefficient. But again, Greg helped us out here and made this way more efficient. So there's now a scheme called magic state cultivation, which allows you to make these T-gates much more efficient. So this was a very important advance for the field. Okay, so I should have kept track on time, but since I'm not sure when we started, so these were sort of the two pieces I wanted to talk to you about: our progress in hardware and our progress in software. And I can perfectly stop here and we can open for Q&A, but depending how much there's more time, I can also amuse you with some other topic, the third part.
That topic, so maybe you can spend another 10 minutes on this.
Yes. Okay, because this is a little bit different in flavor. At Google, we have sort of this concept of a 20% project where an engineer can just do some fun stuff. The engineer thinks it's important. And to me, I have a background in AI and neuroscience, so I'm still very keen to understand, are quantum effects relevant in neuroscience? And if you start thinking about this, you would say, you remarked it earlier, that AI has largely succeeded in its quest to outperform human intelligence, in the sense that I would arguably, probably many of us would argue that, or agree, that the Turing test has passed. I mean, Turing wrote his seminal paper in 1950. Imagine he would have given him a telephone and Gemini is on the other line, and he would have talked to Gemini. He would have never, ever guessed that this is not a human. So in that sense, Turing test solved hands down. But despite the success in artificial intelligence, there are still questions, open questions concerning natural intelligence. Or I should maybe call this natural sentience. Because important questions that characterize the human mind, and the rector was alluding a little bit to that, the question, what generates conscious experience? What happens if I have a toothache? What happens when I smell a rose? Why is there an experience at all? And of course, people used to joke about this question. You can only ask it when you're tenured, because asking that question ruins your career. So I'm old enough that I can now play with this. Also, do we possess free will or not? And so these are open questions that are unrelated to intelligence. And I think quantum mechanics has something to say about these things. And I could derive longer sort of the argument I have, but I will just throw out, since I have only 10 minutes, the conjecture. My conjecture is that a conscious moment occurs whenever a quantum mechanical superposition state forms. Yeah? And people who know a little bit about this field may realize, oh, this sounds like Roger Penrose's idea, who had suggested that a conscious moment is implemented when a superposition state collapses. And actually, my ideas came about when I tried to come up with an experimental test for Roger's idea, but then realized that Roger's suggestion doesn't play well with special relativity. So it's, instead of saying the conscious moment occurs when a superposition state collapses, it's safer to assume it, or to conjecture that it occurs when a superposition state forms. So why maybe just to motivate this a little bit, where is this coming from? Or maybe we leave this for the question session. Let me tell you something more important, that is, how can you test it? Because the interesting thing about this conjecture is it is testable. And to my knowledge, it's actually the first theory of consciousness that is experimentally testable. Why is it testable? So you could think of a setup that goes like this. You have a brain, your brain or my brain, and inside this brain, all sorts of things happen. And on a very low level, nobody would argue that quantum effects happen, at least within molecules, and our electronic structure obviously is governed by quantum effects. So superpositions form in our brains all the time. Roger would say they collapse all the time. So there should be little conscious blip moments all the time, involving, let's say, typically an average like n qubits. We don't know what n is. Actually, I don't think n is very large, because I think conscious experience is more an executive summary of what is going on. And people have tried to estimate it. And if you look in the literature, they estimate it's between 100 bits to 100,000 bits per second. So not very much. So you would complain about your Wi-Fi channel if it had only such a low bit rate. So that's the brain. Then, of course, we have our quantum processor, where it's made to make big superposition states. So let's say it involves superpositions over m qubits. So now, let's at least conceptually, how we do this experimentally, get to it, but conceptually, let's assume we do a coherent link between the qubits, the n qubits in the brain, and the m qubits in our processor. Now we form wave functions and superpositions over n plus m qubits. So if Roger is right, or if my conjecture is right, then the user should feel an expanded consciousness, because it goes from n to m classical bits that the user would have to report about the experience. You know, if a state forms over n qubits, that means if you were to report it, you would need n classical bits to say what happened. And here you would need n plus m bits to report it. And I can possibly make m pretty big. So you go into a setup. You would envision something like an MRI machine, non-invasive. And then initially, hey, how do you feel? Well, like always. How about now? What are you talking about? Then you press a button under the table and then woo. So if this idea is correct. Or, yeah, so it's testable. Moreover, by using user reports, we could obviously collapsing or going into an all-zero state should feel different from going into an all-one state. So the qualia of the experience should be encoded in the configuration, the classical configuration of the qubits. And possibly by steering this correctly, we could on demand shape the qualia of the conscious experience. I want to be euphoric, melancholic, I can do that. So it's a testable theory. But now, I teamed up with neurobiologists and physicists to really make this happen. And they go, oh, Hartmut, come on. Like, how would you possibly do this in practice? This sounds like you can never do that. But then we developed a program, an experimental program, to work ourselves up to this experiment. It's published, it's shown here. And I show you the initial experiment we have been doing. And this is the following. A good way to identify quantum mechanical degrees of freedom in the brain that would be worth coupling to, because we have a physicist on the team called Dirk Bouwmeester. I don't know whether you know him. He's a Dutch physicist, highly decorated physicist, and very down-to-earth, practical experimentalist, who, by the way, also believes that quantum effects are key to understand brain function. And he asked, so do you want to use photons? Do you want to do spins? How do we do the coupling? And then we thought we can do the following. We can use xenon, the noble gas, and expose different biological systems to xenon. Why is this interesting? Xenon is an anesthetic. So you can do surgery under xenon if you have a big gulp of it. I mean, interestingly enough, anesthetics are being used since 180 years. Yeah, it's a medical godsend. Anybody who ever had a surgery or went to a dentist knows about this. Yet nobody understands how anesthetics work. Now, there's a huge zoo of different molecules. They seem to have no common chemical motives. And that something like a noble gas, like xenon, is an anesthetic, points to the fact that anesthesia might have to do more with physics than with chemistry. And by the way, an anesthetic that works on a human works on pretty much any other organism, all the way down to plants, like in mimosa or a fly-eating plants. You can anesthetize those too. That shows that anesthesia must work on a very profound, basic cellular level. So the two systems we use, one is brain organoids. These are little balls of lentil-sized balls of generic brain tissue, and we do electrophysiology and look how the signal changes when we give it xenon. And the second system is to get behavioral data. Let me see whether I can show this here. And I love this experiment because it's so simple that a high schooler can repeat it. Now you have a little syringe here. There are 40 flies in there, and they're buzzing around. And now we'll fill this syringe with 10% air. Now the flies need to breathe, and with 90% xenon. But then we do one more tweak, and that is we don't just use natural xenon, we use different isotopes of xenon. Because there was an obscure paper that claimed that different isotopes of xenon have different anesthetic potency. And if we could reproduce this and show this with good statistics, then this would be a nice piece of evidence to say, look, quantum neuroscience is a thing. We need to consider quantum mechanical effects to understand how xenon works. And anesthetics overall. So yeah, I go a little bit forward with this video a bit faster. So what you saw earlier there, so it's just sucked the xenon in. Now it's a mix. Now it's 10% air, 90% xenon. And at 1 atmosphere of pressure, it's not quite anesthetic yet. The flies are a bit drowsy, but they are still going around. So now we push the plunger in by a little bit, and we increase it to 3 atmospheres. And then what you will see here in a moment, that the flies have become all very sleepy. You can tap a little bit to just make sure. Tap, and then I call it the Glastonbury Festival moment. So they all fall to the ground. And now you pull the plunger out. And then within seconds, you will see, let me accelerate this again a moment. You go a little bit further out, and within seconds, the flies are buzzing again. And again, what we are seeing, even though it's not ready for publication yet, is that there are indeed differences in potency. How quick do these fruit flies wake up if you take different isotopes of xenon? And that would allow us to identify a mechanism where possibly the coupling we have in mind, coherent coupling, could work. And yeah, so with that, I will give you a little flavor what quantum computing may have to do with neuroscience. And I stop here. Thank you.
Yeah, thank you very much. Because of the time, so I think we must be very economic with the questions. So please formulate questions concisely, and I may also ask you to answer them concisely so that we get a few. We also have online questions via Zoom. Okay, but first here in the lecture hall, who wants to go first? It's always difficult to be the first, right? Yeah, there's a question over there. Our balcony.
Okay, so I have a question regarding to your graph that you showed comparing physical and logical qubits. So I'm confused a little bit. Isn't a logical one made up by physical qubits? So in essentially, what is the meaning of the comparison that you did in that graph?
Yeah, but it's made up by more. So in this, you're referring, I think, to this figure here. I try to be concise, but yeah, in the very beginning now, like this figure, I think you're referring to. So a physical qubit, you can also think of a one-by-one array. Yes, you can think of it as a logical qubit over a one-by-one array. The difference of the logical qubits is that they are made up of many physical qubits. Yeah, so larger and larger arrays.
So essentially, the red line means that if you combine some for error correction, the performance is worse than just using a single qubit.
Right. If the code distance here is too small, exactly. Yeah, it's exactly right. It's just this plaquette here is 3 by 3 data qubits. So there you're not better yet than just using a single physical qubit. So you take a step back. But then you make the code distance bigger. Now you're already a little better. You make it yet bigger. And now you're quite a bit better. Yeah.
Thank you.
Yeah, a question from you. Thank you for the talk. And I really liked the last part of it because it's more for me that I understand it. Okay, as a visionary person, how do you see the future beyond quantum physics or AI or anything of this, especially connected to humans, like the benefit of the next after quantum era?
Yeah, this is why I jumped over this picture here, because I thought we leave it for the Q&A session. Where is it? Here. One more. Look, this picture I did with AI. So, so this picture essentially shows a humane version of Schrödinger's cat experiment. And then we don't let the cats have all the fun. We step into this hermetically sealed box ourselves. I invite you to do it. And so to make it not as scary, you don't use a poison, but you use just an anesthetic. I like to work with anesthetics. But then the rest of the experiment is the same as Schrödinger's 100-year-old, maybe not quite 100-year-old thought experiment, where you have this this radioactive atom. It decays. If it does, it triggers the anesthetic. So if we describe this setting and we use the Schrödinger equation, then after some time, if you would open the box, you would only see one of two situations, an awake person or an anesthetized person. And we would have to conclude by just using the Schrödinger equation that both are in the box simultaneously, so that we have a macroscopic superposition of two things. And Schrödinger thought this can't possibly be. He thought this was absurd. And quantum computers, I feel, convince us that this picture of the world, it's called the many worlds formulation of quantum mechanics, is actually correct. Why? See, our qubits are not small. They are about 1 millimeter sized. And the Nobel Prize that's going to be given next week is actually for what they used to call macroscopic atoms. These are macroscopic objects, millimeter size, but they have quantum mechanical properties such as energy quantization. And of course, we don't only have one qubit, we have a whole array. So our chips are not so small. So there's a whole array of things that you can see. And this object we can put into quantum mechanical superposition. Because why do we get these beyond classical computations? It's because in one clock cycle of the quantum computer, we can touch 2 to the 105 things. So we can touch 2 to the 500 things. And this is not a theory, this is not math. This has to have ontological status. These superpositions have to be there, otherwise our quantum computers wouldn't work. So we don't see an easy limit to how macroscopic superpositions can become, and why not humans. And therefore, it offers this very attractive place to put consciousness in a natural or a theory of the natural world that is maybe consciousness is how it feels or how we experience the emergence of a single classical world out of the many that quantum mechanics tells us are there. And I think just grogging this insight, I think will do a lot for humanity.
Maybe let's take an online question now.
We have two ones. So one comment, thanks for the great talk. And are the latest superconducting processors also based on transmon qubits?
Yes.
Thank you. I asked for concise answers.
Make up my time, yeah.
The other one was regarding the coherent coupling between the brain and the quantum processor. So does this mean in practical terms that the idea is to use quantum entanglement between a qubit inside a human brain and a qubit inside a quantum computer? Or am I getting this wrong?
No, it's also yes. Yeah, you want to entangle qubits in the brain with qubits in a quantum processor.
Thank you.
About the consciousness being being superpositional states. Could this also happen in something like plants, because it's also a macroscopic system? So how would we know that there's maybe not like superpositions in something like plants and they could also have consciousness and we just don't know it?
Yeah, I love this question, and you're on the right path. Again, if these ideas are correct, and they may very well not be correct, and I'm a scientist, if the experiments don't come out the right way, I'm happy to scratch the conjecture. But if the conjecture is correct, that the formation of a superposition state creates a conscious moment, then indeed consciousness is not the exclusive domain of brains of higher mammals. It leads to a worldview that's known in philosophy as panpsychism. Essentially, you realize that everything is a little bit conscious because superposition states form in your tea in the morning, they form in a tree, they form in a rock, they form everywhere, so that we are essentially surrounded by a conscious universe. I think that's a direct upshot of these ideas. Yes.
Two questions at the back, one over here. And
hi, thanks for the next talk. So I have a question that's often be asked as well. So you have discussed about the superconducting quantum computing, and there's also other physical platforms like neutral atoms or ion traps or photons. Like, is Google also considering the other platforms, and how do you compare the superconducting circuit to other platform? Thanks.
Yes. See, there's a saying in Silicon Valley that goes like, only the paranoid survive. So we chose at Google to work with superconducting qubits because we know how to initialize them, we know how to do operations on them, we know how to read them out. And if you work, I said this same thing this morning in a Q&A session, that if you would visit our lab and you would walk through the corridors and talk to the engineers, you would get this palpable sense of confidence. Yeah, of course, we will build a big quantum computer. There's nothing really, it's annoying to get the wiring right, but this is engineering challenges that will all be overcome. So we have little doubts that we will get to our milestone 6 and beyond. But as you point out, there are other modalities, how any two-level systems, whether it's photons and this optical fiber and this, or states of an ion, or you can use many different systems to represent qubits, and all you need is to be able to make a superposition of two classical states. And you mentioned neutral atoms. Indeed, that platform has made marvelous progress over the last few years. And you may have seen Google has made an investment in one of the leading companies in the space called QEra, because we wanted to have a first row seat to understand how does their progress and their challenges compare with our progress and our challenges. So yeah, we keep a close eye on all modalities. And our goal is to make a useful quantum computer. The goal is not to make a useful superconducting computer. For now, that's the hypothesis, but we would switch in a heartbeat if any other modality pulls ahead in credible ways.
yeah, two more questions. There was one in the back and one in the front. You're the last.
Yeah, so I'm wondering, how do you come up with such long-term roadmaps for a technology that does not yet exist? So is this using already established knowledge that can lead you to the goal you're trying to achieve? Or is it just a glimpse of fate in a way, where you say, we want to achieve this is the first step, and we think these are the next steps to reach the end goal?
Yeah, that's an excellent question. How do you convince investors, whether it's executives in a large company, whether it's venture capitalists or government or taxpayers, say, hey, give me money. I'm going to build a big useful quantum computer. Trust me. And it took a few attempts, like when I suggested, hey, let's build a quantum computer at Google. The first answer was not yes, for sure. Like it took a few rounds to convince. And the then chairman, Eric Schmidt, he was the first to say, oh, I see where this could be going. But there was a lot of criticism. People came up to me, Hartmut, quantum computing, this is snake oil, this will never work. And there was not exactly enthusiasm. So how do you ensure long-term funding? That's not trivial in any environment, whether in a startup, in a large company, or whether you depend on taxpayers. What I found, formulating a good roadmap where you say, we do this by that year, we will do that by that year, and then you will see this and this, and then you knock out your milestones, hopefully roughly at the times you predicted, that creates trust. And saying, oh, you did this, okay, good, you did that. Next thing is coming up, and as people see you're doing what you say, and they understand why these are meaningful milestones on the way to your end goal, trust is growing, and that's happening across the community. We were probably actually the first ones who put this roadmap up. Now you don't see a single company who wouldn't have a roadmap that looks pretty similar.
Okay. Finally.
Thank you very much.
This is more a philosophical question. The last line of our vision reads unlimited. This is related to unlimited human imagination. But I would like to have your expertise now, also talking about the Wunderkind in your team and all this. Do you think there's limits to the human imagination if you're talking about the superimpositions that form our consciousness, or do you think we can never achieve, or we can never know it?
Perfect. My younger son, he always asks me this question, Dad, is the universe infinite? And I said, we don't know. This is one, I think, of the most profound question. Is the universe infinite in any dimension? Let's say spatial dimension, temporal dimension, the amount of energy on a scale. And the honest answer is we don't know. That's an open question. But one thing I think we can say for sure, I often say it's maybe not infinite, we don't know, but it's exponential. And exponential is pretty big. And for all practical purposes, the difference between a large exponential number and an infinite number, you may never know. So we can maybe get, or quantum AI can get exponentially creative, maybe not infinitely creative.
Okay. I think this was also a very good question to end with. There is also actually Ernst Mach is an Austrian, so also nice that there's also a bow back to Austria here on your slides. Let's all thank Hartmut Neven for this very interesting talk. Thank you very much. Thank you.
Yeah.